Hi, my name is Kanthi Sarpatwar. I'm a research staff member at IBM TJ Watson Research Center, and this is joint work with a few of my colleagues here at IBM. And the title of our talk is Privacy Enhanced Decision Tree Inference. Okay, so here is the broad setting. We are interested in privacy preserving inference on a decision tree based model. Right? So our work falls under a broad framework of privacy preserving inference in a typical machine learning as a service model. So there has been a lot of excitement in this field, and we are contributing to that. So what is a machine learning as a service model? Well, in this setting, a cloud owns a pre-trained decision tree model. In our case, it's a decision tree model, but in general, it is any model, and hosts it on its cloud infrastructure for clients to basically perform inference queries. So client would take their data and send it to the cloud to be and where it is stored, and the results are returned back to the client. So decision trees, we are interested in decision trees here, which in several enterprise settings, decision trees are still considered very important, especially in financial and healthcare sector. I cite a few examples here, and I'll not go into the details. So a key concern, in this typical MLAS setting, ML as a service setting, is the privacy of the client data. So how do we protect client data? The client has to send their private data to the cloud, where so privacy is in question there. So homomorphic encryption offers a very enticing solution in this regard, where clients can encrypt their data and send it to the cloud, where without the need for decryption key, this is the key point, without the need for decryption key, the cloud can perform computations on the encrypted data and return the encrypted results back to the client. So the cloud would not even know what the encrypted results would be, the underlying inference results would be. Right? So there are some key challenges here when implementing this with a decision tree, and that's the focus of this talk. So a brief primer about homomorphic encryption. It's a special kind of encryption that allows certain kinds of computations, such as additions, multiplications, subtractions, and so on and so forth. Right? The key point, as I mentioned, is that it does not require decryption key to perform such computations. Now, it can effectively compute low-degree polynomial circuits, but homomorphic encryption doesn't handle non-polynomial functions in an exact fashion. These include the standard operations such as division, comparison, and sigmoids, or ReLUs, or all these non-polynomial activation functions used in ML. So one has to resort to some approximations for these functions. Another key point here is that consecutive operations accumulate noise in the encrypted results. So when the noise becomes too high, it will become impossible for us to decrypt the results. So one solution to that noise problem is the so-called bootstrapping operation, where the noise is reset in the ciphertext. However, this operation is prohibitively expensive and must be used sparingly. Now, we distinguish two homomorphic encryption schemes. The binary encryption schemes such as BGP and BFE are effective in handling non-floating point operations, or integer or binary operations. On the other hand, the floating point encryption schemes such as CKKS are preferred for limited precision floating point operations. So all these schemes that I mentioned here, BGP, BFE, and CKKS, support the so-called SIMD operations, which allows us to pack several plain text numbers into a single ciphertext. This is called ciphertext packing. and this allows us a great deal of parallelism in operations if one can pack it effectively, do the packing effect. So the key challenge in evaluating a decision tree is the comparison operation. So the binary schemes are effective in doing the comparison. However, they cannot handle floating point numbers, which are needed in typical machine learning applications. On the other hand, CKKS is better suited for floating point schemes such as CKKS are better suited at handling floating point operations. In fact, CKKS has been applied to a wide range of ML applications recently. However, CKKS doesn't handle floating point CKKS doesn't do comparison operation effectively. So the comparison operation becomes very expensive because you approximate it with a very high depth circuit. And this implies we will need the very expensive bootstrapping operations, which on the whole makes comparison a very expensive operation, and we should minimize the number of comparisons that we use. So I'll not get into the related literature and would refer you to the paper. But one thing I would like to point is that the comparison function we use in this work is from this paper by the CKKS inventors. Okay. So this is a core algorithm. This is not the main contribution of this paper, but this is the blueprint we are using. Right? So the key idea is to replace the hard comparison of the decision tree nodes using this soft comparison function. Right? So if you want to evaluate a greater than or equal to b, you simply evaluate a power n divided by a power n plus b power n. And this number would tend to 1 if a is greater than or equal to b, otherwise it would tend to 0. And then you can compute the soft membership of a data point at any given node k in the following recursive fashion. If p is the parent of the node k, then you look at the soft membership of the data point belonging to p, and then do the evaluate b greater than or equal to t, and take a product of these two, and that would give you the soft score for the node k. Similarly, if it's a left child, you modify the computation. Now, a soft membership score is expected to be close if the data point doesn't belong to the node k, and close to 1 if it does. Right? It's easy to see. Now, based on these soft membership scores, it is easy to compute the aggregated class confidences defined in this way. And then finally, the class label with maximum confidence, maximum aggregated class confidence is returned as the true class label, as a predicted class label. I'm sorry. Okay. So coming to our key contribution, we give a novel packing mechanism that effectively exploits SIMD type operations and uses a single ciphertext comparison operation to perform all the comparisons in the decision tree. And this allows us to effectively compute the soft membership for all the leaf nodes. So let me briefly describe what our packing approach looks like. So suppose you're given a depth D decision tree, then for each depth L node, right? So for each layer, suppose a layer is at depth L, and for each node k at depth L, we append the cipher. We pack the following this quantity here, this segment here, into the ciphertext. So we take the value, feature value at depth at the decision node k, and we pack it 2 power d minus L minus 1 times. And we take the threshold value tk and we pack it the same number of times. Right? We also construct another ciphertext which will reverse the order of these two. And the reasoning behind this is quite simple. So we observe that the decision node k belongs to, the node K belongs to exactly 2 power D minus L decision path computations. And for the half of the above decision paths are accessed by comparison Vk greater than or equal to Tk, and the remaining perform the computation Tk greater than Vk. So you can see that that's exactly what, if I compare these two ciphertexts, I'll compare 2 power D minus L minus 1 times of this computation and same number of Tk greater than Vk computations. So once you do the comparison, you get something like this. And now, using a standard rotate and multiply operation, you can compute the soft membership score for all the data points. Again, I refer you to the paper for the exact details of what's happening.